tonight there will be a dinner in the city. So just to confirm, we would like you to sign this sheet if you're interested. So it will be at 7 p.m. at Trattoria Sudan. But please try to sign this sheet if you're interested.
We'll give you more precise indication where the actual restaurant is, don't worry.
Okay, so I think we can start. It is a pleasure to have Enrico Marchetti, right? Marchetto, sorry. Talking about the thermal analytic bootstrap method for holography.
Thank you, Rodolfo, and thank you to the organizers for putting together this nice workshop. Today I'm happy to tell you about this work that we did together with Julian Baran, Dennis Boscourt, Alessio Miscioscio and Enrico Moni. Notably, Dennis, Alessio and Ellie are all together here and also in the first line of the talk. And Dennis has a poster on this project, so if you have any questions, feel free to bother her with questions as well. These are going to be the two papers I'm going to talk about, one for the analytic methods and one for the application to holography. And basically in this project we've been interested in studying the dynamics of massive scalars in ADS backgrounds hosting a black holes, or the focus of this talk in particular, black brains. We have some results for black holes, but this talk will be only about black brains in ADS. And we know that if we use the ADS CFT correspondence, these systems are dual to conformative theories that live on manifolds of finite volume and where the time has been compactified on a thermal circle. While black brains are an infinite temperature limit of this system, so deprived of any phase transition, and they live on what I'm going to refer to as the thermal manifold. These are flat space times a thermal circle. What is in the bulk? Well, I will kind of already decided that we have Einstein gravity coupled to a massive scalar, and the metric is going to be simply the black brain metric in EDS, where the corrective factor is connected to the Hawking temperature. Curvature correction can be accommodated for, but they're not going to be the focus of this talk. We can discuss it if you want. What we are interested into is to study, well, the dynamics of this scalar field, and this means studying the wave equation of this scalar field. Well, this is a formidable challenge by itself, so we're going to focus on a smaller problem. If we focus on the solution of this wave function close to the boundary, we are going to look at the correlation function on the thermal manifold of the scalar field on the CFT, which is dual to this massive scalar in ADS. So we're going to look at this. So we're going to zero distance from the boundary, and we're going to look at this object. Of course, what is the relation? Well, I don't have to say to spend many words, but the relation between the mass of this scalar field and the conformal dimension of this object, of this scalar on the CFT, is simply given by the usual holographic dictionary. So now that we specify what is the theory of gravity in the bulk, we want to understand what is the dynamics in the CFT. And we will start by specifying what are the operators that survive the large N and large coupling limit that you're forced to take if you want to explore Einstein gravity in the bulk. So let me start by being very schematic, at the risk of being redundant for many of you, but this redundancy will prove to be very useful for understanding. So let me classify the operators that survive the large cap and large N limit by conformal dimension and spin. And the first operator, of course, is the identity operator, which has 0 conformal dimension and 0 spin. And then we have two more classes of operators. One is going to be the double trace class of operators, which is labeled by 2 quantum numbers. You can loosely see this semi-classically as, well, maybe you don't see it here, so let me write it a little bit lower. semi-classically, you should see this as the double twist operators that you build with two scalar fields, n boxes and L derivatives. The conformal dimension is simply given by 2 delta phi plus L plus 2n, and the spin is given by L. And then the third class is going to be given by the multi-stress tensor. Also, these have some spin L, and these you should see them semi-classically as the composition of a number of stress tensor, in particular n stress tensor, where a number L of indices is left uncontract. And these instead are going to have the dimension D, the dimension of the conformal field theory, times n, and spin L again. Okay, the first the first thing worth of notice in the holographic setup is the fact that the conformal dimensions of all these operators, if we choose delta phi to be at least half integer or integer, as it will be the case of this talk, are all going to be integers.
Sorry, can I ask another question? So in principle, you would also have triple traces and right, phi cube.
Well, we are considering only the large n, the infinite n limit, so all these operators would come with 1 over n correction factors in front, so these are dropped. In the limit where I have only these effectively filling the bulk, if I start including the vertices in the gravity theory, those operators will also appear.
So the thermal correlator is not sensitive to this?
In this limit, no. If you
This
start,
is specific EFT. This is not the thermal correlator in general.
like if you start including corrections to your gravity action, these will appear.
So if, but because I guess you want to connect this with the thermal correlator at the end.
Yeah, exactly.
So in
Like,
principle, this is an approximation, but you will need to include more.
No, maybe let's put it like this. This is whatever is the holographic dual of this naive theory. So
Okay.
this is not n equal to 4 supernion mills. We will talk maybe more in the discussion how to improve upon this, but for this is what you have.
Yeah.
In principle, if you would go to higher order in the correction, there will be higher traces. No, this is the
Exactly.
It's all
high.
Exactly.
What is a bit surprising is why don't you have? This is also for n equal to 0, I believe. So you also have the stress tensor by itself.
Yeah, of course.
Okay.
So like maybe instead of thinking of an holographic theory from the top down, so starting from a string theory and then compactifying, so taking KK0, KK mod, etc., you should see this as a holographic from the bottom, so from the bottom up, so taking Einstein gravity and then just adding massive scalar and then seeing what happens. This kind of, if you want, the approach that was taken by Fitzpatrick and Wang in the 2019 paper, which I'm also going to refer to later in the talk. Very good. So if delta phi is half integer or integer, then all these conformal dimensions are integers. Very good. And this spectrum is going to be the input for our problem. And now we want to study how the OP of these two scalars encoded this spectrum. And in fact, what I want to do is to highlight the existence in the OP of three families with similar properties. So let me consider the OP of the two scalar fields, and let me categorize this OP in terms of the conformal dimension of the operator that appear. So they're going to be delta equal to 0, delta equal to 2, delta equal to 4, delta equal to 6, delta equal to 8, and let me go even further, and then I stop delta equal to 10. So at delta equal to 0, we only have the identity operator, and that's it. Delta equal to 2, there is no operator appearing. And let me now specify delta phi equal to 3. For the sake being, this reasoning can actually be generalized to any integer dimension. Why am I choosing parentheses integer dimension? Well, ideally, I said before that I'm studying bottom-up holography, but ideally I would like to connect these results at the end of the day with n equal 4 superior meals, other theories that incorporate in the spectrum scalars with integer dimension. So these are the scenario that I want to study, and then I am going to go further. The stress tensor appears. At delta equal to 6, we don't have multi-stress tensors, but we start having the first double trace operator. At delta equal to 8, we start having the double trace tensor with spin, with different spins. These are going to be 0, 2, or 4. And then the double trace operators with 2, 0 or 0, 1. And then at delta equal to 10, we don't have again any multi-stress tensor, but we have double trace operators with their collection of boxes with collection of derivatives. So now I can highlight 3 different families. I first highlight this family, and I'm going to call it number 1. What is number 1? Number 1, and I'm going to write it here so it stays. Number 1 is a collection of a finite number of multi-stress tensors, light, because they come before the first double trace, that are not degenerate with any double trace operator. So I'm going to call this a finite number of light multi-stress tensor, non-degenerate with double trace. Then I have a second family, which is given by these operators here, which are double traces. These are an infinite number of double traces because they go over and over in the OP, but they're never degenerate with any multi-stress tensor. And this I'm going to call it number 2. So here we have an infinite number of double traces, never degenerate with multi-stress tensors.
What about T squared with a couple of derivatives inserted?
Sorry?
What about T squared with a couple of derivatives inserted?
This is higher.
Well, this will arise a bit.
Delta equals 10, right?
Delta equal to 10. Yeah, maybe this I forgot. But in any case, you will see this pattern reappear. You will have.
But then the last one can be degenerate. We shouldn't be encircling it.
This one, yeah, will be degenerate with this. But in any case, unless you have a very specific delta phi in your problem, you will always have like some double traces which are never like degenerate with multi-stress tensors.
Yeah, the first one.
So
Delta equals 6, sure, is not degenerate.
this is just an example to show you that there are some there are a finite number of multi-stress that arise at the lighter dimensions. There are some multi-stress tensors that are degenerate with double traces, and then there will be some double traces that are never degenerate with any because of incompatibility of the conformal dimension. And in fact, this comment gives me.
Just a question. Are you now working on a sphere or are you working on R?
I'm looking at flat space times time of circle.
Okay.
So the idea of the number 3 is that now we have multi-stress tensors which are degenerate with double trace. And these are going to be an infinite number. Very good. So now that I highlighted these 3 families, and I decided to take as an input the spectrum and large N and large coupling, I would like to understand if it is possible to reconstruct the full correlator out of this information.
Sorry, what comment about the term family, can you lift it by saying that delta phi is generic, like instead
Yeah, sure.
of being
Absolutely, absolutely. If delta phi becomes non-integer, there is no degeneracy anymore between multi-stress tensor and double traces. In fact, if you start including one of the random corrections to your gravity action, to your gravity theory, this degeneracy will be lifted. So what I'm talking about, I would like to stress, is a peculiar setup that holds only in the strict large geometry. Okay. So now I'm going to use some analytic methods to bootstrap, to reconstruct the whole correlator out of the information given by these families. But first, let me give you some elements of CFTs at finite temperature. And I'm going to start by considering the CFT on the thermal manifold. Okay? If I start considering the CFT on the thermal manifold, I'm going to introduce a new scale, which is beta. This is going to break the rotation invariance, and it's going to allow a whole class of operators to develop non-zero expectation values. I would like to investigate to tell you what the CFT at finite temperature inherits from the CFT at zero temperature and what actually changes from the point of view of DOP. So let me further draw a cartoon of a plane. This plane contains theories, and the CFT at zero temperature populates the critical point at zero temperature. This could be also a conformal manifold, but let's say that it's a point for the time being. Nothing changes if it's a conformal manifold. The CFT at finite temperature is going to be the one populated by this line, and this is that it's CFT at zero temperature. What does the CFT at finite temperature inherit from the CFT at zero temperature? It inherits two things. First of all, it inherits the spectral data. And by spectral data, I mean the spectrum of the operators and the structure constants. And then it inherits the structure of the OP. This means that if I take the local product between two operators, it will decompose into the same collection of operators as it does in flat space. Very good. What happens instead is that this OP is not anymore convergent at infinity. In fact, we have to use our Omni scale to say that now the convergence of the OP is dominated by the scale beta. So this is going to be the distinction between the OP at zero temperature and distinction and the OP at finite temperature. And now that we have the scale available, a whole class of operators will develop a one-point function. By a symmetry argument, in fact, even though we broke down the dilatation, we still have some leftover symmetry that we can use to say that only symmetric, traceless operators with even spin will develop a non-zero one-point function. How will this look like? It will look like, well, beta to the delta O by dimensional analysis. It will have the fixed kinematic structure, which is going to be by E1, Ej. These are vectors, unit vectors in the time direction, minus traces. And then it's going to be a dynamical information, which is the only theory-dependent element, in the form of a new number called thermal one-point function, which must be added to the CFT data of your theory. How does the fact that this one-point function now are arising modify the decomposition into OP of the correlator in which we are interested from the beginning? So we can consider this general configuration, where this is the thermal circle, this is the flat space, and I'm going to place the two operators at two different points on the thermal manifold, separated by a distance tau over the circle and a distance r on the spatial directions. It's not necessary to specify the direction because the spatial rotations are still preserved. So this is going to give me this two-point function, which can be decomposed according to the OP, which is still preserved, as follows. So I'm going to have some dynamical data given by this coefficient, AO. These are simply the product of the three-point function, which is still available, and the one-point function that I just introduced. And then the kinematic part will be a block, thermal block, which is known. It's going to be x. So actually, let me say tau squared plus r squared square root is to the delta O minus 2 delta phi. And then a Eigenbauer polynomial. If we are in dimension 4, it's going to be 1 here. And then we have tau over square root of tau squared plus r squared. Okay, very good. So now every operator in the OP has its own OP coefficient. If this was at zero temperature, only the identity would develop this structure, and the rest would be 0. But then the thermal block is too complicated for my purpose. So I would like to have a thermal block which is slightly easier.
Sorry, another question. So I cannot redefine b theta by changing the normalization of the operator. There is a canonical normalization of the operator, yeah.
Yeah, consider that you want the stress tensor to always have the same, it is fixed since it is connected to the central charge and to the free energy of your theory. So you cannot change the one-point function in the stress tensor because if you change the free energy.
Yeah, but that's not the stress, that's the generic operator. Right?
Yeah, but then word identities would constrain this one-point function to be fixed. When the stress tensor enters these word identities, then the normalization is chosen.
Excuse me. Sorry, you're saying that this b theta cannot be derived from those CFT data. So it's something.
No, I'm not saying this.
Ah, no, you're not. Sorry.
But this is an extremely good point. The one-point function should actually be seen as a function of the
this was my question.
Data at zero temperature. How would you get that? Well, you would have to consider the one-point function at zero temperature as a sum of all the states in your filtered space, in particular at finite volume, so you can use the state operator correspondence, and then evaluate this density matrix against the operator, and then divide by the partition function at finite volume. You are free to do that, and you will find that this one-point function is a function of the original spectral data. What happens is that this is actually extremely difficult to perform. So the convenient choice is to treat these numbers as a full-fledged new data for the bootstrap problem at finite temperature. Okay, so I was telling you that this block is too difficult. I don't like it. So I'm going to change the configuration, and I'm going to place the two operators on the same thermal circle. I get rid of this coordinate, and my block ends up being simply tau to the delta minus 2 delta phi. And here, notice that I implicitly selected beta to equal to 1 without losing, without loss of generality. But now I'm paying a price. I simplify the block, but I'm paying a price at the dynamical level. Because now I don't have one-point functions univocally associated with the operator. I don't have OP or coefficient univocally associated with one operator. But I have a new coefficient which runs over all the conformal dimensions appearing in the OP, defined as follows. So what is happening here? I'm taking all the coefficients of the operator sharing the same conformal dimension, but with different spin. I'm weighting them against these Gegenbauer weights, and then I'm considering their sum as the 1-point function, the coefficient. This never happens in strongly interacting theories like Ising, Grossner-Yukawa, because the spectrum is never degenerate. But this happens in holographic theory, so we need to consider this. And in fact, this is actually welcome, because it solves a problem. And what is the problem? It's a tension in the OP. Because now I'm going to introduce the second input of our problem, which are the OP coefficients of multi-stress tensors. Okay? So I have this OP coefficient for multi-stress tensors. These were actually computed from the gravity point of view, solving the wave function close to the boundary and assuming the spectrum to be the large N spectrum. How does this one OP coefficient look like? Well, the first one for the stress tensor is going to be pretty easy, but then as soon as we go to higher points in the multi-stress tensors, we have this structure. So a generic function of delta phi, and let me be schematic for the time being, and then a pole structure that looks like this. Etc., etc. You go higher in order in the multi-stress tensor, these poles simply expand. So now it would look like if you plug these OP coefficients in the OPE, and you choose delta phi to be an integer, this OPE diverges. So this would be the naive expectation. But actually the fact that you are dealing with the degenerate spectrum simplifies your life, actually solves this problem. Because the mechanism now becomes the following. I consider the contribution to the OP from the multi-stress tensor. And let me be schematic again, let me call it like this, where I'm highlighting only the pole that I will encounter since I'm sending delta phi to N, where N is an integer. And then its block is going to be simply a polynomial, that I'm evaluating it in the conformal dimension of the multi-stress tensor minus 2 delta phi. But these multi-stress tensors are going to be degenerate. With what? With the double traces that I highlighted before. So now I have to consider only also a degenerate contribution. In order to not to have a divergent OP, at the end of the day, I have to have the same coefficient here, but then I also have a regular part in the OP coefficient. And now this is going to be evaluated, the power in the conformal dimension of the double trace minus 2 delta phi. Okay? And then I take the limit for delta phi going to N, and the pole simplifies because I developed a logarithmic contribution to the OP. So the problem of having the poles in the OP is simplified, is taken care of by the fact that 1 and 2, these families where this degeneracy does not happen, will have this contribution to the OP. And instead, the operators that are all degenerate in conformal dimension and participate to the family number 3 will instead have appear with a logarithmic contribution. Sure.
So, imagine you wouldn't have done this, but you were in the example that you were showing before with the Gegenbauer polynomial and so on.
Yeah.
And you would have done things
Yeah.
the usual way, you would have gotten the same result.
Yeah.
Meaning that.
Yeah.
So this is like a concept. You could have done that in the proper way, and then you would have gotten that you have two sums because you have to take care of these two families of operator, and you would have gotten here.
Sure. Like what you are liking is something I glossed. At least I glossed a little bit over. This mechanism where you develop logarithms in your OP would appear also if you were in the previous configuration. Why am I focusing on this configuration? Because at the end of the day, I want to reconstruct the full correlator. And these blocks are the ones that allow me to do it exactly. If instead I was using the previous blocks, I would not be able to do the same procedure that I'm going to show you now. It would be more complicated, and we can also talk about it. But you're right in highlighting the fact that this mechanism would arise also if I was at spatial distance. It's just that I'm trying to choose these blocks in order for the following part to be easier.
No, but I wanted to be more positive than this in the sense that you were saying that this is just an approximation, but this is not true in the sense that it's not just an approximation, it's something that you would have gotten either way.
Yeah, it's not an approximation, it's just a simplification of the
It's a
setup.
simplification, but a good one in the sense
No,
that,
it's good. It's
it's
good.
more than what you were saying, I believe, or at least I understood it was.
Yeah. Okay. Thank you for the remark.
So you would get also logs for finite partial separation.
You would have it. You would have those as well. The number of operators that participate to each logarithmic contribution will be smaller because then you also have to have degeneracy in the spin. This happens, of course, because like the multi-test tensor, they can have also spin matching the double traces. The important thing is that you always have at least two operators degenerate in spin and component dimension.
Can one understand these logs from coming from some anomalous dimension, or isn't it strange that you have some logs in the OP device?
Okay, so many papers have been studying the case of delta pi integer from the gravity point of view, solving the very function, a la Fitzpatrick 1 if you want. Also in this case, Fitzpatrick 1 solved it assuming that delta pi was not an integer. If you assume that it is an integer from the back, you will end up with logarithms. And you will not be able to solve your wave function without assuming an ansatz with logarithms. Now, can they be interpreted as an anomalous dimension? Some people did. Some people interpreted them as an anomalous dimension for the double trace operators. But I don't think that this is the interpretation that I prefer. I think that these logarithms are a pathology or a feature, if you want, of the strictly Lagrangian limit. And in fact, these logarithms have a physical consequence, as I will try to show you later. Only because these logarithms appear in the OPA, you then develop the bouncing singularity. And only because you have the bouncing singularity, you develop an arc contribution that then you will see. It has a gravitational mean. So I would say that these logarithms are not to be interpreted as anomalous dimension because the spectrum is the spectrum of Lagrange without anomalous dimension, and they have a physical consequence.
Okay, isn't there not even like some algebraic, like maybe some log CFT read and some noise? They're just pathologies of the.
No, I wouldn't say so. I wouldn't say so. If you want, like if you want me to try to be open to more possibilities, what one could try to see if there are mixing between operators. So are we actually using, when we consider the spectrum to be double traces, multi-test tensors, as I liked it before, are we considering this basis to be the right basis to do this computation in? If you ask me, I would say yes, but it is possible that there are mixing that we are not taking into account. It is also possible that...
I mean, they're going to appear somewhere, even if you don't mix them. The basis is complete, they're going to have somewhere.
Yeah, but maybe some people could tell you that this is a mixing problem. It's actually a very discussed problem at the moment in the community.
Yeah, when there's external operators as stress tensors, then you can interpret these logs as coming from anomalous dimensions. The anomalous dimensions are one when suppressed, so that's why you don't see them here, but there you will see.
Okay. Thank you.
But
Okay.
don't they also come from this sum that you have over there? And this comes from the fact that you have infinite sums.
The logarithms.
Yeah.
Well, at the moment I would look at them more as a regularization, the outcome of a regularization. Infinite sums will arise, so infinite sum,
No, down there, like you were denoting this
Here.
A delta, so secretly there is an infinite sum that you are doing.
well, not really, no, because for each delta, whatever big it is, the sum of the spins will always be finite. So fix your delta, the spin is going to be fixed as well.
Also the coefficient AO have the same, I mean, he explained for this one, but AO has the same problem. So
Yeah,
for the
it's,
sum, you already have logs.
Exactly.
Sorry, so am I right in thinking that there's the regular piece you can't fix by this method, right?
Yeah, like the regular piece at the moment is not fixed. But I would like to, if I manage, at the end I would like to convince you that it is possible to fix it using more bootstrap conditions. But at the moment it is not known in general and it is, you don't know what it is. Okay. Okay, so now that we collected our result of the different OP contributions, let me try to reconstruct the whole correlator. And to reconstruct the whole correlator, I'm going to consider the analytic structure of this correlator. And if I focus only on the real axis, I know that the only poles are going to be the ultraviolet divergences that arise at 0, 1, 2, -1, -2. What are these poles? Well, I'm considering these configurations. When one of the fields rotates around the thermal circle, it stumbles upon the other fields multiple times, and these are the poles that arise from that. But then I can complexify the tau coordinate. And now these poles are poles in a complex plane. And remember that I have in my OPE logarithms. And logarithms require the introduction of some branch cuts, which are attached to these poles. And I decide to draw in this way in order to have an ending result, which is parity and periodicity invariant. In particular, my two-point function, if I call it g tau, will always have to satisfy this condition, which goes under the name of KMS condition. Very good. So now that I laid down the analytic structure of this correlator, I can use Cauchy formula to rewrite it. So I fix a point tau, I take a contour, and then I blow up the contour, going to consider the integral over all these contours around the cut, and then the integral on the contour at infinity. And I'm going to call the integral over the contours on the cut number 1. And then number 2, the integral over the arc. Actually, let me address immediately the one of the arc. For the time being, let's say that this is just a function of tau. I'm going to be more specific later. Let's focus on the more interesting part for the moment, which is the integral over all the cuts. The Cauchy formula returns a sum over all these integrals, which looks like follows. and we have a kernel. So this is going to be called the dispersion relation, and it is equivalent to the integral over all these contours. And notice that this sum is already looking a lot like a sum over thermal images. And I'm not integrating the whole two-point function, but only the discontinuity of the two-point function. So now I only rewrote the two-point function. Can I actually provide dynamical information? I can, because it's all contained into my OP that I already described. So what I'm going to do is the following manipulation. I'm going to rewrite the two-point function in the OP decomposition. I can do it. We are in this setup where the OP is always convergent, because the two fields are never more distant than B. And so I open the OP. These are going to be my generic thermal block. And then I invert the discontinuity with the sum over the OP. If you want to complain, you can do it. I have an answer for it.
Then we don't complain.
So now the discontinuity is either acting on a polynomial or it's either acting on a logarithmic contribution. So either polynomial or log times polynomial. And this is going to be for operator number 1, operator number 2, and this for operator number 3. How does the operator number 1 look like? So the operator number 1, we said that it would have been a finite number of like multi-extension, never degenerate with double trees. So I have a finite number of delta is less than 2 delta pi, and I have delta. And then the discontinuity integrated over the kernel and summed over images returns this contribution. Look, we took care of the thermal images sum, and in fact our function is manifestly k-less invariant. Very good. And we introduced this function, which is the Hurwitz theta function. Let me spell it down here for you. Okay?
Sorry, can I ask you?
Yeah.
I have a stupid confusion. I'm used to think about when I have a small special separation,
Yeah.
then I would have two branch cuts going like, I mean, I have the 2 points and I would do this up and down. And then I'm used to think of the fact that, I naively think that when x goes to 0, I cannot really go out to the strip of analyticity without crossing a branch cut. But if I draw what you're drawing, it seems that you actually can. This is
So the point is that you always have analyticity in the full complex plane if you retain the sum of the thermal images. Because the sum of the thermal images is simply a sum over all the strips, and in each strip you have analyticity. In this moment, where I performed the sum of the thermal images, I chose one specific strip.
and you copy it all.
And the result is only holding in this strip that I selected. If you want, you can write the result in another strip, but it will simply be translated. But the point is that once you perform the thermal images sum, you should not expect an analyticity error.
But then the sum is, so the correlator in a single strip, it seems from the drawing that you can actually extend it all over the complex plane without crossing, like it's completely analytic in the full upper half plane.
Well, this is actually, I understand the confusion.
But it wouldn't be the case for small x, right?
So if you consider the small spatial separation, which is, this would be the structure of the cut.
Yes.
And then you bring it down, and you are basically connecting the two cuts.
Yes.
For computational purposes, it would you would compute the integral over these two contours. But then these two contours give the same result because of time reversal.
Mm-hmm.
And then you would have to divide by 1/2 to normalize the value of the one-point function of the identity. So yeah, and then you would take the limit for delta x going to 0. So at the computationally wise, it is the same to do this. It is important to keep in mind that the analyticity is, once I write down the block of with zeta function, is confined to this state that you chose.
But you can still move around. It seems that maybe we can discuss later, but from what you drew, it seems you can still move around the whole upper plane without ever crossing a branch curve. So it seems that you're analytic much more than just inside the sphere.
I think that if you focus on analyticity, your picture is better. My picture wants to illustrate the way in which you compute the dispersion relation, but I think that if you want to focus on the issue of analyticity, your picture is better.
But maybe you can. What is the difference between these two pictures? In the sense, I would expect the second as analyticity structure. So, what are you doing in your picture?
So in this picture, and in order to so let's start from this one. I would compute the integral over the whole contours.
No, but sorry, before. So what? So this is the green function. So what are you drawing there?
What I'm drawing here.
So what is this object that is analytic in the upper plane?
So like the correct object would actually be like an object where you have cuts that go from minus infinity to plus infinity. Because this is the limit of this picture.
Yes.
However, like the way in which I perform the computation is to ideally take the two contours from the upper branch and the second branch. These two contours by time reversal are the same, so I can consider one only and then take the limit. So consider this picture, the limit of this picture for analyticity purposes, and consider this picture if you want to understand what kind of computation I'm performing at the moment.
Okay.
Okay, so computationally wise, this is the outcome, and this is going to be, how much time do I have?
10 minutes.
Okay, I can make it.
13.
Okay, no, it's good. So this block that appears in the two-point function is not a random block, but it's simply the thermal correlation function of a generalized free fields with dimension the half of this. So this, I would like actually to call it the GFF delta phi minus delta 2 tau. Okay? So at the end of the day, my contribution number 1 is simply going to be a finite sum of generalized free fields blocks, each weighted by the one-point function of the operator of the multi-stress tensor. Okay, now we can go to family number 2. This was an infinite number of double traces, never degenerate with multi-stress tensors. And it still enjoyed this OP block, this timer block. So this is going to be the answer again. But once you plug the double trace spectrum, you will see that you have to compute the Hurwitz zeta function in a negative even integer. And this makes it vanish. So operators from number 2 family never contribute to the dispersion.
This is just a statement that you have tau to some integer power because zero discontinuity, no?
Yes, exactly. It's exactly equivalent. So the number 2 never contributes to the discontinuity, while number 3 is going to contribute to the discontinuity using these blocks. I can simply evaluate their contribution to the dispersion relation by taking the same regularization procedure, not for the OP contribution, but for the generalized free fields blocks, and this simply gives me a sum over an infinite number of operators of conformal dimension, where the block is not the GFF block, but its derivative in the first argument. And this is the dispersion relation. If we want to have the full correlator, we simply have to add the arc contribution. Okay, so this is the final formula for the correlator. And let me comment on one thing. So we said that the number 2 family of operator never contributes to discontinuity, but we still appear in the OP. And how does this family of operator appears in the OP? So it will appear from thermal images, from the fact that from here, and it will appear from the arc. So this is eventually where we find the infinite number of non-degenerate double traces in the final outcome of this computation. At the moment, this is not really useful, so I would like to give you some insights on each one of these pieces. The first insight that I want to give you is about the first part, which is a finite sum of generalized fields. If we select delta phi to be equal to 3, then this is going to be the identity and the stress tensor. So it's going to be GGFF 3 tau plus the 1.5, the OP coefficient of the stress tensor, times GGFF 1 tau. You can make an experiment and plot this 2-point function against the numerical solution of the full wave function that I wrote at the beginning. The discrepancy is 1.3% at its peak. And I invite you to go to Denis' poster, because you will see the plot where these two lines are plotted against each other. So 1.3% discrepancy at most, one could say that this is already a nice, quantitatively measured like this, approximation of the full holographic correlator. But then let's try to understand what is this contribution and this contribution, because it's where the gravitational physics arises.
Sorry, can I ask you something? The
Sure.
GFF block evaluated at this point contains a log tau, right?
At this point,
Yeah, if you take the block, at least the 4-dimensional block, it contains a log.
no,
It does not contain, so this is just a power.
This is just the sum of the images of inverse power to some.
So no logs.
No logs. Logs appear here. In fact, this is what I'm going to talk next about. So I would like to evaluate this. I would like to evaluate. Is it 10 minutes? Okay. I would like to evaluate this piece, but this accounts for infinite contribution. To do this, I have to approximate, and here the work of Andrei, Sam, Nates comes useful, because in their work they provide asymptotics for large delta of these OP coefficients. And we can use them, similar to how they did, to evaluate this contribution. And in particular, if I call delta for n, where n is an integer number, it's counting the number of stress tensor in the multi-stress tensor, this is going to be approximated by some numbers for n to the 3 plus n to the third. And we can use this, we can make the approximation of using these asymptotics for all the multi-stress tensor appearing in this contribution and get an outcome. To get an outcome, I have a sum over operator of a conformal dimension and a sum over thermal images that is hidden inside the computation of the GFF. Let's swap them for the time being. I will not be able to perform both of them, but I'm more interested in resumming an infinite number of operators rather than resumming an infinite number of thermal images. And if I perform this operation, I end up with this. So a sum over thermal images a logarithm appears, as I knew it was 90, and then a pole structure appears. And these are the famous bouncing singularities highlighted in Andrei, Nate, Sam work, in Christopher as well, in Robin work. And these are placed, for example, in these points on the complex plane. We had these poles, which are the physical one, and the position of this bouncing singularity depends only on the dimension v, and in this case, in v equal 4, they appear here, in the middle of the strip, reflected and then repeated.
So where does the discontinuity come from?
The discontinuity here? Well, you are, in order to compute this, you have to take the discontinuity of a logarithm times a polynomial. The discontinuity of the polynomial itself would be 0, because you are above 2 to the 5. But then you use Leibniz rule. The discontinuity of the logarithm would be 2 pi, and then you're left with a polynomial that then you integrate over the contour.
Well, that's where the log comes from. Where does the log come from?
So, but the logarithms here. Well, the logarithms here, it comes from the fact that here, like you are considering derivatives of the GFF in the first argument. So consider that the GFF it's kind of inheriting the definition of the U with theta function. And in order to consider the derivative, you're taking a derivative of this with this variable, and so the logarithms.
But basically, it comes from the sum, not from the original log.
Exactly, exactly. So in fact, here I exchanged the sum of the thermal images with the sum of the ROP, because I'm more interested in summing over infinite operators rather than thermal images. Then if you are able to resum this, you get the full thing, but we are not able at the moment.
Yeah, but this is just a leading term. Will be
Yeah, this would be really different. Okay, so now we have the following, that the infinite sum, the sum of infinite operators, the multi-stress tensors, produced an extra pole in the middle of the strip. This was only possible because we were summing an infinite number of operators. How do we compensate for this? This bouncing singularity should not be in the final outcome. We need to find an infinite sum, a sum over another infinite number of operators. And where does this come from? From the arc, which is encoding an infinite number of non-degenerate double traces operators. Double trace. How do we compute the double trace? Well, we have already this expression. We can take the expression for the thermal image number 1. And this is going to look like a sum of the poles, where we have a leading pole, which is going to be computed in the bouncy singularity with a leading power plus subleading poles. And this is simply a matter of performing the same procedure that Andrei and collaborators did in their paper of last year, taking the arc contribution as minus the sum of their images of these poles. In this way, you are engineering an arc contribution that for sure cancels those divergences. And this will end up, we boil down, being like another sum over GFF correlators, but not computed in tau, but computed in tau minus c. And this basically ends, yeah.
Sorry.
Sure.
Can you elaborate a little bit on how you computed this again?
So,
Maybe it was too fast.
of course. So this would be what you get if you compute this contribution by swapping the sum of the delta with the sum of the thermal image. Then you focus on the first strip, so you set n equal to 0, and you identify the position of the bouncing singularity. Then you expand this in series, this term, around the bouncing singularities, and this produces a finite sum of poles, where the leading one is the one with this power. Then what you do is take this sum of the poles, take these poles, sum it over images, so plus m minus tau c. Take the second pole, sum it over images.
No, but I thought you were going to explicitly compute the arc contribution somehow. So why is look, it looks like you're just canceling this pose. Right?
Yeah. It looks like it is exactly what I'm doing, and one then would ask why this should provide the final answer. Why the arc contribution is simply fixed by this procedure. Very good. It was actually probably the final part of my remarks. At the moment, in this way, we engineered a total function that is KMS invariant. And has the same analytic structure of the correlator, of the physical correlator, because I simply compensated the bouncing singularities. Now, am I allowed to add another function of tau to this total correlator? Can it be? In principle, I could. So how can I be sure that this procedure fixes the correlator? However, if I add another function, f tau must be entire, because otherwise it spoils the analytic structure that is already fixed. It has to be periodic. And with these two conditions, one could prove, using a generalization for periodic function of Liouville theorem in complex plane, that f tau is a constant. And this constant at most modifies the one-point function of the operators that appear with 0 power, which is the first double trace. Okay, maybe it's not enough, so we need to add another thing, which is clustering. I take my 2-point function, I look at the 2-point function of the imaginary axis, and then I ask the 2-point function, when k goes to infinity, decomposes into the square of the 1-point function of the original external operators, which usually is 0, because in realistic holography these are charged operators. Okay. But then this will fix the constant, and you will get the final outcome to be uniquely fixed. Uniquely fixed given the input that we used, which was the spectrum of large n, and the OP coefficients given by the Fitzpatrick and 1 procedure. If you modify these conditions, you will still be able to apply this formalism. But you will not have these logarithms, and you will not have these arcs. Because in the arcs, there will be no other operator appearing. Because the operators, double traces, non-degenerate, appear in the arc only because they are dropped by the Hurwitz zeta function. So maybe it's a good moment to stop.
Okay, thank you very much. And I guess we can naturally move to the discussion. So any question?
Okay, so just about the philosophy, I guess. You're using bootstrap, but you said that you fixed the theory to be a specific holographic model. So that's just because you don't want to numerically compute these quantities?
No, the bootstrap sets a framework that then can be used for whatever the spectrum, etc., etc. also notice that actually by doing this, I'm deriving some dynamical data. Because I said that I was using as an input the OP coefficients of the multi-stress tensors. But I never said that I was using the OP coefficients of the double traces. And now, like all those double traces that were not degenerate with multi-stress tensors, I can simply expand this expression in OP and I get an outcome. And I get an answer for that. So I also bootstrapped dynamical data by doing this.
For those you could just compute using the theory you used to derive the
Yeah, like if you want, I'm using the word bootstrap as in its interpretation of like given a certain input about the theory, I'm going to bootstrap its 1.5.
Okay.
It's not the interpretation of given as a space of theory, I put some rigorous bounds on which theories are physical.
Sorry, can't you also think in the way that, for instance, at the beginning you were listing all these operators that you have.
Sure.
You would start with this assumption, saying I have these families of operators. How would
That's precisely
Yeah.
the point.
the consequence of having these classes of operators?
Yeah.
You have the double traces, the stress tensor, even
But
if you don't know the theory you are coming from, no?
Also, the transparent one will not give you the double trace. So this
No, but-
method is like a way to take
But
as input that and get.
But in principle, one could compute the double traces
Of course, if you can
from the
solve
same
wave
theory that
equation.
you get the stress tensor contributions.
Right, right, of course.
I'm just saying the input here is the stress tensor contributions.
Yeah.
But
And
those come from a holographic model. The holographic model also gives you the double traces. So it's going around in a circle in a sense. But okay.
But the holographic model, but it doesn't give you the double trace, you know?
It does in principle, it's just difficult to compute.
In principle, ciao.
Sorry?
You have to find a way to compute it.
You just solve the
And
wave
that's,
equation on the black hole background.
Yeah.
And that's it.
But,
Yeah, like in this specific case, yes. Like if this, like, because in principle, consider that you can actually give a more complicated spectrum.
Yeah.
And you tell me, for example, the first OP coefficients of light operators, which are maybe the easiest one to compute using the gravity cycle. And then I would tell you that you can control the approximation that you make it by truncating, because in that case the sum over the operators would be infinite. And then you have a good approximation for all the other OP coefficients of the spectrum.
I agree, like the stress tensors are much easier to compute, but I was just wondering about the philosophy. But yeah, I think I understand. Thank you.
More questions?
Yeah, curiosity. So you were taking as an input the large small n of the stress tensor, right?
The asymptotic model for these OP coefficients. Yeah.
So if you take one of the small n correction, what would that correspond? Does it produce subleading singularities of the bouncing, like 4 minus 1 instead of 4 or something else?
No, like if you take 1 over n corrections of this, you will still have bouncing singularities.
But the exponent would be lower or higher?
Yeah, exactly. Like you will modify, like you will still have a leading term, which is given by the leading term of Andrei and collaborators, but then you will have another contribution. It's not. You will get rid of the bouncing singularities if you introduce 1 over n corrections, the big one.
Yeah. No.
But not if you introduce these kind of corrections.
I was wondering if small n correction, if the small n expansion can be easily translated into an expansion of tau, like maybe you're, I don't know. But okay.
Yeah. I will expect the subleading powers and the OP coefficient and the coefficient of the subleading pose to be dependent on the correction that you make to the asymptotic model. Actually, probably Ellie will talk about it, and you can also check Denise poster. There is a pathology that derives from using asymptotic model for all the operators, that is the lack of boundedness. But the expectation is that if you correct your asymptotic model, you will eventually recover boundedness. So the outcome is highly dependent on this.
In the second contribution, right? So is this, so where you take the asymptotic model, does that also contain the contributions of double traces that are degenerates to?
Yeah. Like as I said at the beginning, like you should see this OP coefficient as the degenerate sum of all the operators that have the same conformal dimension but different spin. So you will not be able to disentangle these from this expression. The way in which you should do it is to include the spatial distance.
Yeah, no, so the one thing I wanted to ask, right, so because you're inputting on only the data for the stress tensors, right? But there is in
Correct.
principle double traces which you don't get in. Do you make any mistake by that? Like basically like...
As I was telling you, like the 1.5, the OP coefficient are associated with double traces. The ones that are degenerate with multi-stress tensor will have a pole part.
Okay.
This pole part must be equal to the one of the multi-stress tensor with a minus inside, in front. Otherwise, even after regularization, you end up with a divergence.
Okay.
They also have a regular part, which now you're able to compute, because this regular part will come from expanding this part, and by maybe expanding also this part, maybe. I have to check. But for sure from this part. So now that regular portion of the OP coefficient that you didn't know about, you can get it.
This might be very intuitive. Imagine you have your correlator, no? This would give you the 2-point correlator.
Yeah.
Now you could, imagine you have it in a closed form, like a function, no?
Yeah.
And then you say, okay, now forget the way you derived it. I want to expand it in blocks and read off the information about your theory. Are you able then to disentangle the 3 families you started with or not? Like the families that are degenerate at this order, at this level.
So if I have the correlator,
Like
you're asking
imagine
me
you
if
have
I have
the correlator, nobody
spectrum.
tell you how you compute it. And now you want to read off the spectrum of your for your double trace together with the T and also the one that have the same dimension.
Yeah.
Because it might be, I mean, the reason why I'm asking that is to go back to Christopher's comment, no? Like, would you then be able to see these logs somehow, or?
So yeah, like if I had this God-given function and I expand it into blocks, I would expect to find polynomial blocks and blocks with the logarithm in front. And this logarithm in front would be associated.
But how would you interpret them? Because then you don't have any logarithm if you would write them in terms of regular, generic blocks, no? Because you told me before that the blocks are only polynomials. So how would it come because you don't even see the logarithms if you have the full correlator, no? Because those are cancelled by this arc part.
If I compute fully this this part, I end up with logarithms.
But then how would they come from the blocks you would input, no? This is my question. Like if you have the function, then you have to write that as a sum over the double trace plus a sum over this Tn plus the light, you know?
Yeah.
But then how do you see, how can you see the logarithms from the block point of view? Because then you don't have derivatives, you are a leading order. Sorry, maybe it's completely naive, just in case you thought about that. It might be that it's trivial, the answer.
So I think that you need to see the blocks in any case, whatever is the correlator, because if you don't see the blocks, then if you don't see the blocks, all your blocks are polynomial. And then if all your blocks are polynomial, if you...
No, that's exactly my curiosity. Like your blocks would all, in principle, they seem to be all polynomials, so how can you find the logarithms?
Well, in the moment in which I solve the degeneracy between the double traces and the multi-stress tensor, the ones that are affected by the poles in the oblique coefficients, I am forced to retain logarithm. I am forced to have logarithm. If I imagine to have a two-point function which does not have logarithms in its expansion for a small tau, then I apply the same procedure of computing the special relation, and it naturally ends up being a finite sum of GFF contribution. So if I don't find logarithms in my two-point function, I'm simply finding I'm forcing my two-point function to be the composition of different GFFs disentangled between each other. Of course, this is always a pathology of Lagrangian limit, because if you are not in Lagrangian, strictly Lagrangian, you will not
this I understand, yeah.
Okay.
So for this whole procedure to work, it was crucial to have delta phi being integer.
It was not necessarily crucial. In fact, if you want to do half integer, basically you will forget about this, and this sum is not anymore a finite sum but an infinite sum. And this sum itself produces the boundary singularities, and then the arc contribution is fixed in the same way. In fact, we tried to do it for your, and we found the same answer.
So it's crucial for delta to be either integer or half integer, so
Exactly.
that your poles disappear at some point.
Exactly. If you were doing 3D easing, you would have an infinite sum of these, but nothing in the arc.
So half integer is even easier. You don't have to worry about the logs. You just sum over images, then you cancel the poles, and that's your unique answer.
Yes.
Yeah, that's what we did.
Exactly.
I have another log comment, maybe sorry, but if I take a current at zero spatial separation, is exact, and I the function of omega, if I transform, I don't see any log. But it's also true that there I'm at fixed spatial momentum, so somehow I'm integrated out of space. Do you expect it? Would you expect to see a log there or not?
In the momentum space.
No, I'm saying like if you take the arc current in momentum space at zero spatial momentum, then you get an exact function of omega that is very simple, and you can just Fourier transform it.
But
Yeah.
that's also n equals to 4, right? There's a difference between large and CF and n equals to 4.
But it's when I go for large n.
Okay, let's say we are doing this. Let's just say wait.
Sorry?
We are doing this, so
Okay,
wait.
Okay, so maybe it's a good moment to move to informal discussion. Let's thank the speaker again.